Bismillahirrahmanirrahim. Now, this is the lecture number 3 of the ongoing series of the Structural Analysis 2 course. Today, we will analyze the statically indeterminate frames using the flexibility method. We already solved the indeterminate beams using the same method. Today, we will apply the same method to the indeterminate frames with some modifications and with some more knowledge for you guys to learn. So let's start with the topics of this lecture. Initially, we will introduce this method for frames. We already did it for the beams, but today we will do it for frames. We will review some prerequisite topics for flexibility method. We will discuss them as they are necessary for you guys to know before you start doing the flexibility method for frames. We will also discuss the stepwise procedure for this flexibility method. We will discuss each step. We will not discuss in quite detail, as we will then be doing an example problem on that. So in example problem, we will be then discussing each step in detail, and we will be applying that on an example frame structure. And you guys will see that how the flexibility method work in case of frame structures. We'll also do another example and then a third one also. So in today's lecture, as this is your first online lecture of this Structural Analysis 2 course, so we will go a little slow today so that you guys adjust with this new method of learning or this new way of learning. So then we will end up with the references. So we'll try to cover till example problem number 1. We'll try to cover this problem number 1 in quite detail today, and then in the next class, inshallah, we'll start doing these other problems. Okay, so
now let's start with the introduction. The flexibility method is also called force method. This method is actually a generalization of the Maxwell-Moore method, which was developed by J.C. Maxwell and O.C. Moore. In this approach, statically indeterminate structures are analyzed by writing compatibility equations in terms of flexibility coefficients and selected redundants. The flexibility method is presented in a matrix form, and the advantage of writing it in matrix notation is that it serves to organize the work and helps to avoid errors. The basic steps involved in the flexibility method for frames are the same as already we did for the analysis of statically indeterminate beams in the previous lecture. We will be taking only the bending deformations. Here is the axial deformations are very negligible. Why they are negligible? Because the frame members are very rigid actually. So if we compare the axial deformations of the frame members with the bending deformations, so they are so small that we neglect them in our analysis. Our basic aim in the flexibility method will be to find out the internal resisting axial force, the shear force, and the bending moments which are developed due to the applied external load on the frame structure, and thus to draw the shear force and bending moment diagrams for each frame member.
okay, what are the topics that are necessary for you guys to know before we start the stepwise procedure? Is that how to find the static indeterminacy of a rigidly jointed frame. So as we discussed in the very first lecture of this structural analysis 2 course, that the static indeterminacy of a frame structure can be determined by using this equation, which is 3 times b plus r minus 3 times n. Now, what is b, what is r, what is n? So let's discuss them. B is the number of frame members. So you are actually multiplying the frame members with 3. What is R? R is the number of support reactions. So if there is a fixed support, it means there will be 3 reactions. If there is a pin, so there will be 1. If there is a hinge support, there will be 2 support reactions. What is N? N is the number of joints. N is the number of joints. So if you look at this equation, 3b plus r is giving you the total number of unknowns, whereas the 3n is giving you the number of available equations. So total number of unknowns, which is coming from 3b plus r, if you subtract from it the total number of available equations, so you know actually the remaining number of unknowns, that how many remaining number of unknowns are there, which cannot be solved using the available equilibrium equations. So how we know the number of unknowns? What are the unknowns? As we know that the main aim of this analysis is to find out the shear, the axial forces, the bending moments, so at any section of the member. So it means that for each member we are taking 3, which means axial, shear, and bending moment for each member. So that's why we are multiplying the total number of frame members with 3. So those internal, you can call them the shear, the axial, the bending moment, they are the internal unknowns, and then the support reactions, they are also the unknowns. So when you add them, you get the total number of unknowns. And what is 3n? N is the number of joints. It means that the total number of available equilibrium equations can be found by multiplying the total number of joints with 3. So let's apply this. Let's apply this on a problem so that you can get a better idea. We have a member, we have a structure here. We have a frame structure here. So what is B here? B 1, 2, 3, 4, 5, and 6. And what is B? B is the number of frame members. So we have 6 frame members. 1, 2, 3, 4, 5, and 6. Okay, what is R in this case? R in this case is, as we know, the R is the support reaction. So we have 3 support reactions at this support and 3 support reactions at this support. So the total number of support reactions, which is denoted by R, this will be equal to 6. And what is N? This is R. R is equal to 6. What is N? N is the total number of joints. So how many joints we have? We have this joint 1, we have this joint, we have this number 3rd, we have 4th, we have 5th, and we have 6th joint. So we have total number of joints equal to 6. So if we plug them in the equation, in this above equation, which is 3b plus r minus 3 times n, so we get 6 degrees. Now this 6 degrees means that there are 6 unknowns. There are 6 unknown reactions which cannot be solved using the available equilibrium equations. So in order to solve them, then you have to apply some other conditions. You have to apply some conditions of compatibility then, so that in order to solve them, in order to find those unknowns, and then using the once you find the values of these unknowns, then you are able to solve the rest of the structure using the available equilibrium equations. If you have any problem, you can ask at any point. You can stop me. Okay, the next structure, if you look at this structure, we have the total number of frame members equals to 10. So how we do this? So look at this: 1, 2. This is third member, fourth. This is fifth, sixth, seventh, eighth, ninth, and 10. So we have 10 members, and per member we have 3 unknowns. So that's why we multiply each member with 3 in case of 2D frames. So this is 3 times 10. This is 30. And then we add with this. What we add with this? We add with this R, which is the total number of support reactions. So how many support reactions we have now? We have 3 support reactions at this point. We have 3 support reactions at this point, and we have 2 support reactions at this point. So we have this vertical support reaction. We have this horizontal support reaction. We have this bending here, bending resistance at this point, bending moment. So 3 at this point, 3 at this point, and 2. So what is missing here? Here the bending resistance is missing here. This support cannot resist moment. So it means that there can be no moment developed at this point. So the moment will be 0 at this point. So it means the support reactions are 3 plus 3 plus 2. Totals are now R equals to 8. So when you add with the already known unknowns here, the 3 times 10 plus this 8, so you get 30 plus 8, 38. So there are 38 unknowns in this frame structure. Right? So, and how many available equations you have? So you have 3 times the number of joints, 3 times 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is 9 into 3 is 27. So if you subtract from 38, if you subtract 27, you get 11. So there are 11 number of unknowns in this frame structure, which cannot be solved using the available equilibrium equation. Okay, so I hope you all are getting this. So we proceed to the next. If you have any problem, so you can ask here. Okay, now let's review the next one. In case of beams, we used a method which was the conjugate beam method for finding the displacements at various points. In this method, we will be using the unit load method. You must be familiar with this unit load method from your Structural Analysis 1 course. In this analysis course, we will be using it quite several times. The formula for this unit load method is given here. Now, what are the different terms in this formula? What is I in this case? There is a summation from I equals to 1 to n. What does it mean? I is the current, I shows the current member. So if you have a frame member, a frame structure having 2 members, so this I, when I is equal to 1, it means that you are talking about the first member of the frame structure. When I is equal to 2, it means you are talking about the second member of the structure. It means that you will start from the very first member and you will end up with the n, and n is the total number of members in the structure you are considering for the analysis. So when I is equal to 1, you are applying this equation, this term, this whole term to this integration term to the member number 1. When I equals to 2, you are applying the same term to the member number 2. And this summation means that you are then adding them. You apply it to the first member, you have the value, you keep it, then you apply it to the next member, and you add with the previous value, and so on. You move to the next, to the next, until the total number of frame members are solved for this term. Now, you know the I, you know the N. So what is this capital M? This capital M is the bending moment equation. It is the bending moment equation. You know what is the bending moment equation? It is in terms of some unknown length. We sometimes denote that length by x. So if you write the bending moment equation for a member in terms of x, for which member? For the member which is under the consideration, member I. And this bending moment equation should be due to the externally applied load. So when you apply the given external load on the member, and you write the bending moment equation for that, that bending moment equation will be denoted by the capital M. And you need to put that equation in this equation. Now, what is the small m? The small m is the same bending moment equation, but there is only difference in this, and the difference is in the load. In the previous case, we have applied the given external load on the member. In this case, for the small m case, we will apply a unit load. We will apply a unit load. So if you are finding the displacement at any point P, so in order to find the bending moment equation, due to the externally applied load, this formula, this equation requires you to find out the bending moment equation due to the externally applied load, also due to a unit load applied at the same point P, and you find out the bending moment equation in terms of x, and then you put it in this equation. Okay, what are the other terms? You know, N, we already discussed it. It is the total number of frame members. What is E? It is the modulus of elasticity of the member I, which is in the consideration. And I is, of course, the moment of inertia of the member, which is under the consideration. So this is the equation we will be using for finding out the displacement in various steps in this flexibility method. We will discuss it in more detail there also, so that you can better understand the concept there. So the same method we will be using for finding out the flexibility coefficients also. In one of the steps, there is required to find out the flexibility coefficients. As you already know, in case of the beam case, we did it by doing that conjugate beam method. So we will develop the flexibility matrix, flexibility coefficient matrix, by using the same equation as we already used. But there is only a difference in the case of in the previous case, there was a capital M, but in case of flexibility coefficients, we will be using the small m both times the small m. So it means that there will be no you will not need to write any bending moment equation due to the externally applied load. You will both times you will be writing the bending moment equation for the member due to a unit load. So mj means that the bending moment equation when the unit load is applied at the point J, and mk means that when the unit load is applied at the point K. I'll make it more clear through a problem which we will be solving. The remaining things are the same as on the previous slide. So we move now to the stepwise procedure, which involves the very first step is the determination of the degree of static indeterminacy. So now you know that how you can find out the static indeterminacy for a frame structure. So in the very first step of this analysis, you are going to find out the static indeterminacy. Once the static indeterminacy is known, so what you can do after that, you can so what you get from the first step, you get the total number of unknowns which cannot be solved using the available equilibrium equations. So now those unknowns, those extra unknowns, can be 2, can be 3, can be 1, it can be any number depending on the structure you have. So then in the second step, you need to choose the redundant constraints. Now, why I have used the term choose here? So this word choose means that if you have the static indeterminacy equals to 2, so it means you have 2 extra unknowns, but these 2 are not the only unknowns in your structure. There will be several more unknowns in the structure depending upon the supports you have. So it means that in those total number of unknowns, then you have to choose any 2. If you have static indeterminacy equals to 2, so you have to choose any 2 support constraints, which makes your analysis easier in the coming steps. So you have to very wisely choose those constraints, and then you have to release them to obtain the basic determinant structure. So as these 2 extra unknowns are making your structure indeterminate, so once you release them, by releasing them, it means that your structure becomes determinate, and such structure you call it basic determinate structure, BDS. I'll be using BDS quite many times in the coming slides. So BDS will mean that the basic determinate structure. Okay, also in this step 2, you need to calculate the DRS. You need to calculate the DRS. Now, what is the DRS? The DRS are the values which corresponds to the initial support settlement. Now, if there is any support settlement or support rotation corresponding to the chosen redundant location, so you need to record those values in a matrix which you call DRS. So depending on the redundant constraints you have chosen, if corresponding to those chosen constraints which you have released, if there is any support settlement or if there is any rotation, so then you need to record them in the form of a matrix which you call DRS matrix. Okay, so now in step number 3, you perform the analysis of the BDS, and the BDS is again the basic determinant structure which you obtain by releasing your chosen redundant those constraints. Now you need to analyze this BDS under several conditions. Now you know that in the formula we discussed for displacement, there was a capital M, there was a small m. So how you find those moment equations? So here we study that in the capital M can be which is the bending moment equation in terms of x, and under which condition? Under the condition when the BDS is subjected to the external load. As you know from that slide which we discussed, and that equation for the displacement, that this m corresponds to the bending moment equation due to the externally load applied. So where you apply the external load? You apply the external load on the basic determinate structure which you obtain from the step number 2. So, and then you write the equation in terms of x. So in terms of any variable you can use, but that variable should be consistent throughout your analysis. Okay, the small m, the same procedure. You can apply this. You can apply the same procedure with one exception, and that is instead of this external load, you apply a unit load, and due to that unit load you find out the different, the equation that for writing the moment. So in terms of x, so you write that equation in terms of x, and then you move to the next step, which is the step number 4. The bending moment equations which you have written so far, you arrange them in the form of a table. Also, you arrange the other given data, and this arrangement makes your work efficient. Why efficient? Because you don't need to go and again and again, you don't need to go back and see what is there for m, small m, what is there for capital M for each member, because you will have you will have many members. You will have many frame members. So for each member there will be capital M, there will be small m. So in order to avoid the chances of error by going back and see the values of m, small m for each member, if you write all of them in the form of a table, and the rest of the data also in a table, so it will be easier for you to apply then the unit load method in order to find the deformations. Okay, so now the next one is to calculate the values of the DRL. What is DRL matrix? The DRL matrix are the values which corresponds to displacement at the redundant locations. So if you find out the displacements corresponding to the chosen redundant locations in the BDS due to the externally applied load, this is what you call a DRL. So the capital M value, which we have obtained from the step number 3. If you look back here in step number 3, we found out this capital M value and also the small m value. So if you put them in the equation which we studied earlier for the deformations through the unit load method, so you then obtain this DRL matrix values in this step. So you need to know the capital M value from the step number 3, the small m value from the step number 3, and you need to put it in that equation for the deformation in order to get the values of this DRL matrix. Okay, in the next step, then you have to find out the values of the flexibility coefficient matrix, and the flexibility coefficient matrix are the same deformations, but the deformations are due to the unit load applied. So at one time you apply a unit load at one redundant location, and you find out the deformations corresponding to the other redundant locations. So then you, in the next step, then you again applied a unit load at the other redundant location, and in the same way you find out the deformations at the remaining redundant locations. This gives you the flexibility coefficient matrix. Okay, in the step number 7, you have now all the matrices that are required to find out the values of the unknowns. This AR, it corresponds to the redundant actions. So the redundant actions are actually the extra actions which are the unknowns. So this unknown can be then, it can be, we already did it for the beams method. So you can then determine it by using this equation. So in this equation, we have F, which is the flexibility coefficient matrix. We have the DRS. In the very second step, we solve this DRS, which are the values of the support settlement or rotations corresponding to the chosen redundant actions. And this DRL is the matrix we obtain by applying the external load on the BDS and then finding out the displacement corresponding to the redundant locations. In the step number 8, we then solve the members for shear force and bending moment diagram, and we apply this equation. What are the different matrices? What are the different matrices? AML, AMR. So AML now here, we don't need, we are not doing anything with the displacement here. We are doing everything with the member end actions here. So these are the different member end actions. This AML are the member end actions when you apply external load on the BDS. and this AMR is these are the member interactions when you apply unit load on your BDS. So how you do this? We will now clear all these concepts, all these steps in quite detail here through this problem number 1. So I'll be going very slow in this problem. Okay, so now this is the problem number 1. We'll discuss it in very detail, and we'll apply each step. So this is the frame structure which is given. This is the member number 1. The length of this member or the height of this member is 15 feet. The second member, which is supported, which is having a hinge support here, and the length of this second member is 30 feet. This is the joint A. This is the joint B. And this is the joint C. Talk about the loadings. So we have a 5 kip load, external load acting at this point B here. And we have a uniformly distributed load acting on the member number 2. And the magnitude of this UDL is 2 kip per foot. So now you need to analyze this structure using the flexibility method. Step number 1, find the degree of static indeterminacy. What was the equation for that? 3b plus r minus 3n. How many frame members we have? 2. One with a length of 15 feet and second member with a length of 30 feet. So we have 2 frame members. What is R here? Number of support reactions. So we have how many support reactions we have? We have 3 support reactions at this point, this support. Which are there? This vertical, this horizontal, and this bending moment. Right? These are the 3 support reactions at this point. How many support reactions we have at support C? So we have this vertical and horizontal. As it is a hinge, so we don't have any moment here. So the total number of support reactions are 5. Now, what is N? N is the number of joints. And 3 times N gives you the total number of available equilibrium equations. So the number of joints are 3. As we know, A, B, and C. These are the 3 joints. So if you plug it in this equation, right, all these values, so you get 3 times the number of frame members plus the support reactions minus the available equation. So this gives you a static indeterminacy of 2 degrees. Okay. It means that out of these several unknowns, there are two extra unknowns which we cannot determine by using the equilibrium equations. Now, what are the unknowns? So if you look at the unknowns here, the first unknown is this 3 into 2. 3 into 2. These are the internal unknowns of these members, of these frame members. 3 unknowns in this member, 3 unknowns in this member. So it means that 3 per member, so 3 into 2 are 6. So these are the 6 unknowns. And 5 are these unknowns, 1, 2, 3, 4, and 5. So it means that out of these 11 unknowns, we cannot solve 2 unknowns with the available equations. I hope you are getting my point. Now, why I'm doing it, I'm explaining it so deeply here, is because in the next step, as you know, step number 2, we have to choose the redundant constraints. So you can choose now, you should choose now wisely in these unknowns. These are the unknowns. We just release the number of support reactions. We just go into these constraints. We want to release them. So if we want to release them, this will make the analysis a bit faster and easier for you guys. So we have to choose now among these 1, 2, 3, 4, and 5. Okay, so step number 2, we have to select the redundants. Redundants are the extra constraints. And we have to then release them to obtain the basic determinate structure, the BDS, right? The BDS. So how we do this? This is the, now we have a choice. We can choose any of them. This is 1, this is 2, this is now 3, this is 4 here, and we have a 5th one here also. These are the 5 unknowns out of the 11 unknowns. So we want to choose among these 5. So you can choose any of them, but you have to remember that if you choose any 2, so your structure should be able, you should be able to solve your structure efficiently in the remaining steps. Is because when you release any of the 2, any 2 of them, you are going to obtain a basic determinate structure, and this basic determinate structure you will be solving it quite many times in the remaining steps of this method. So you have to make this decision very wisely so that your structure should be efficiently solved later on. Okay, so what I do, I solve now I solve it by choosing these 2 constraints, these 4 and 5. So I release. It means that if I choose these as redundants and I release them, releasing means that there will be no effect of these reactions in this structure. So if there is no involvement after releasing of these reactions, so it means that this total support, it will vanish. There will be no support at this point then. So you will get a free end at this point. So let's do this. I choose these 4 and 5 as my redundants. And what I do, I release them. It means that the support from here vanishes. There is no support now at this C. At C now we don't have any support. Now it means that this is now our structure which we have obtained by releasing the two extra unknowns. Okay. Now in the next step we need to write our redundant actions. So corresponding to each constraint you have released, you need to write a action which we call as the redundant action. Now this is AR1. This is our redundant action. This is not a constraint, remember. This is not a constraint. This is an action. This is just an action which is unknown. This is a force which is unknown. And this force is in the direction of the constraint which we have released. Okay, similarly, what we have released, what else we have released? So we have also released a horizontal constraint. Now, corresponding to that horizontal constraint, we need to put another action which we denote by AR2. So remember, these are not constraints. These are actions, unknown actions, redundant actions, which we have placed corresponding to the constraints which we have released. Okay, so now if we move forward, okay, now in the second step, we also need to compute the DRS values. So the DRS values, which are the support settlement or rotation corresponding to the chosen redundant action. Now we know that now these are our redundant actions, right? AR1, which is acting upward, AR2, which is acting towards the right horizontally. Now you can choose this AR1 to be acting downward also. You can choose it. You can choose this AR2 to be acting leftward also. This totally depends on your choice. So you can choose it pointing towards any upward or downward, leftward or down, this rightward. So, but this should correspond to the constraint. This should correspond to the constraint. So as we know that our reaction number one, which we have released, was pointing upward. So I have chosen this to be acting in the same direction, AR1. And as we know that the second one was acting thisward, so I chose this to be acting towards this rightward direction. Now I need to find out the support settlement. So if it was given that this support at C, it settles down, it means it settles down vertically. It settled down vertically by 2 inches, let's say by 2 inches. So it means that there is a support settlement corresponding to AR1 direction, because AR1 is pointing upward now, or vertically. It is a vertical action, redundant action. Now if there is any vertical displacement in this, vertical settlement in this support, then we have to route them corresponding to the redundant action 1. So as we are given that there are no support settlements, we have no support settlements, we don't have any support settlement at this C downward, we don't have upward, we neither have any support settlement upward. So it means that the DRS value, the first value of the DRS matrix, which will be corresponding to the redundant action number 1, it will be 0. So we wrote here that the DRS1 value is 0. Now remember, if there was a support settlement, which we'll be discussing in the problem number 2, there will be a settlement in the support. We will be taking that. So we will then discuss that in detail there also. But if there is any settlement in this support downward, so it means your AR1 is acting upward, support is settling downward. It means you have to then choose. You have to write negative. You have to write negative with the settlement then. And if it is settling in the direction of your chosen redundant action, then you will write it with the positive sign. Okay, similarly, corresponding to the redundant action number 2, AR2, is there any translation of this support? Is there any translation in this support? So translation means that towards left or towards right. So we are given that there is 0 translation in this support. It means that the AR2 value will also be 0. So if there was any translation, if there was a translation towards the right, the value would have been positive, is it would have pointed in the same direction of this AR2. Or if it was leftward, then the sign would have been negative with that. Okay, now this was the step number 2, but we are left with only one thing, and that is to obtain our finally basic determinant structure, our BDS. So what will be our BDS? Now let's see that. This was the given structure. What we do now, actually, what we do now is to remove the external load. We have removed the external load, both of this 2 kip per foot and also the 5 kip point load. And we also release this support. You have seen this. This is a support, and we release this. So now this becomes our basic determinant structure. This is our BDS. So whenever in the coming in these steps in this lecture, if I talk about the basic determinant structure, so you should automatically remind that we are talking about this structure. If I say that apply the external load on the BDS, it means you need to apply the external load, which was 2 kip per foot, and this point load on this BDS. So if I talk about the point load, so you apply then a point load on this structure, right? So when you apply a point load, it means there will be no external load applied. And if you are applying an external load, it means there will be no unit load applied at that time then. So they will be covered in separate steps here. So now let's discuss them in the step number 3. Now this is the